Welcome all to the online lecture series on applied electromagnetic theory. In this video lecture, I'll be dealing with the topics from the first module of AET and myself Rinju Marin Raleigh, Assistant Professor, Department of ECE, Rajagiri. So far we learned about electrostatic fields, but this video lecture will introduce to the topics of magnetostatic fields, especially Biot-Savart's law, Ampere's circuit law, and its applications in an infinite line current and in an infinite sheet of current. The prerequisites needed are vector calculus, magnetic field intensity, and Stokes theorem. From the previous lectures, you already understood the basics of electromagnetic. It's all about the study of charges. And I already mentioned under electromagnetic theory, we have electrostatics, magnetostatics, and electrodynamics. An electrostatic field is produced by a static or stationary charges. But if the charges are moving with constant velocity, a static magnetic field is produced, or that is a magnetostatic field. So from this video lecture onwards, we will focus more on magnetostatic fields. When the charges are moving with a constant velocity, that will result in a static magnetic field. Or we can also say a magnetostatic field is produced by a constant current flow. When we learned electrostatic field, there were two major laws. What were they? Coulomb's law and Gauss's law. Similarly, in magnetostatic field, there are two major laws. They are Biot-Savart's law and Ampere's current law. Where Biot-Savart's law, that is a general law of magnetostatics, whereas Ampere's law is like a special case of Biot-Savart's law, and it is easily applied to problems that involves symmetrical current distribution. So Biot-Savart's law, it's analogous to Coulomb's law, and Ampere's law, it is somewhat analogous to Gauss's law. Biot-Savart's law. Biot-Savart's law states that the magnetic field intensity dH produced at a point P by the differential current element IDL is proportional to the product IDL and the sine of the angle alpha between the element IDL and the line joining P to the element. And it is inversely proportional to the square of the distance between the point P and the element. So we have the magnetic field intensity directly proportional to the product of ideal and sine of the angle alpha and inversely proportional to square of the distance, that is r square. So dH is equal to k ideal sine alpha by r square, where k represents the constant of proportionality and its value is equal to 1 by 4 pi. So substituting for k is equal to 1 by 4 pi in this particular equation, we get dH is equal to ideal sine alpha by 4 pi r square. The same expression we can represent it in vector form. That is, vector dH is equal to ideal cross AR divided by 4 pi r square, where this represents a cross product and AR represents a unit vector. So substituting for a unit vector, we get ideal cross R divided by 4 pi r cube, where AR is equal to vector R divided by magnitude of vector R. That's why we are getting this ideal cross R divided by 4 pi r cube, where dH represents the magnetic field intensity at point P. In order to determine the direction of the magnetic field intensity, there are two rules, right hand rule and right hand screw rule. So figure A, that shows the right hand rule, and B represents the right handed screw rule. So the direction of dH can be determined by the right hand rule, that is case A, with the right hand thumb pointing in the direction of the current and the right hand fingers encircling the wire in the direction of dH. So the direction of the fingers represents the direction of dH. That represents the direction of dH. Second rule, right-handed screw rule. This is also to determine the direction of dH with the screw is placed along the wire. So this is the screw that is placed along the wire and pointing in the direction of current flow. So this represents the current flow and the screw is placed along the direction of current flow. And the direction of advance of the screw. So this is how the screw rotates. This is how the screw advances. So the direction of advance of the screw is in the direction of dH. So this is the direction of dH. So in order to determine the direction of dH, either you can go with right hand rule or you can follow right-handed screw rule. So if the magnetic field is out of the page, that is represented like this. Okay, this circle with a dot. And if the magnetic field intensity is into the page, then it is represented like this, a circle with a into mark inside. When we learned electrostatics, we had different charge distributions like a point charge, line charge, surface charge, volume charge. Similarly, we can have different current distributions: line current, surface current and volume current. Figure A, that's for line current, B represents surface current and C represents a volume current. Example. So let K denotes the surface current density, that is unit amperes per meter. So the unit itself says this is current per meter. J is volume current density. It's measured in amperes per meter square. That means J is current per meter square, current per area. So the current element IDL is similar to KDS. It's also similar to JDV. KDS, K represents current per meter, current per unit length, and ds is area, okay, that is meter square. So what you will get, amperes per meter multiplied by meter square, that is ampere meter. What is the unit of IDL? Ampere meter. So that means KDS is similar to IDL. So similarly, if you substitute for J and dV, you will get this is also similar to ampere meter. So when we learned Biot-Savart's law, we got an expression for dH. So how to find the total magnetic field intensity? That is by integrating. So for a line current distribution, we have the magnetic field intensity H is equal to integrating over the entire length L, IDL cross AR by 4 pi R square. If the current is surface current, then we have H is equal to integrating over the entire surface KDS cross AR by 4 pi R square. Because here we understood IDL is same as KDS. And H is equal to integral over the entire volume V J dV cross AR by 4 pi R square for a volume current. And here also J dV same as IDL. And A cap R represents the unit vector. And R is the distance between the point P and the current element. Ampere's circuit law. Ampere's circuit law states that the line integral of the tangential component of H around a closed path is same as the net current enclosed by the path. That means the circulation of H is equal to the net current enclosed by the path. In integral form, we can write it as closed integral H dot dl is equal to I enclosed, that is current enclosed. Ampere's law is easily applied in order to determine the magnetic field intensity when the current distribution is symmetrical. This is the mathematical expression for the Ampere's law. So using this expression, you can easily determine the magnetic field intensity H. Ampere's law, it always holds true whether the current distribution is symmetrical or not, but we can use this equation to determine the magnetic field intensity only if the current distribution is symmetrical. Otherwise, it won't be that easy. The statement of Ampere's circuit law, in integral form, we can represent it as closed integral H dot dl is equal to I enclosed. By applying Stokes' theorem to this expression, to the left hand side of this expression, we will get I enclosed is equal to closed integral h dot dl. Now let's apply the Stokes' theorem. Is equal to surface integral del cross h dot ds. But we also know the current enclosed in terms of the current density is equal to surface integral j dot ds. So let's compare this equation number 2 and equation number 3. Here we have current enclosed as surface integral del cross h dot ds, and from here we have I enclosed is equal to surface integral j dot ds. Let's compare what you will get. So from here we have the term del cross h and here we have j. So when you compare these two equations, we get del cross h is equal to j. So this is actually the Ampere's law represented in differential form or in point form. And del cross h is equal to j is the third Maxwell's equation. So that's important point to be noted. And when you observe this particular equation, you can see del cross h is equal to j, and the j value, it can never be 0. That means the magnetostatic field is not conservative. Applications of Ampere's law. Just now we learned Ampere's law. And Ampere's law is mainly used to determine the magnetic field intensity for symmetrical current distribution. Here we apply the law in mathematical form. You learned it is closed integral h dot dl is equal to the current enclosed. And Ampere's law we can apply only for symmetrical current distribution. So for symmetric distribution, the h is either parallel or it is perpendicular to the element dl. When magnetic field is parallel to dl, that implies the magnitude of magnetic field intensity is constant. So now we will see how to apply Ampere's circular law to an infinite line current, to an infinite current sheet, and to an infinitely long coaxial transmission line, and how to determine the magnetic field intensity with the help of Ampere's law. Infinite line current. Consider an infinitely long conductor carrying current I along the z-axis. This one. The path on which the Ampere's law is to be applied is called Amperian path, something similar to Gaussian surface when we learn Gauss's law. So here we have Amperian path. We choose a concentric circle here as the Amperian path, and h is constant provided the rho is constant. So now let's apply Ampere's law. So here we assume this concentric circle encloses the entire current flow so that we can apply the Ampere's law. We know the basics of Ampere's law, that is closed integral h dot dl is equal to current enclosed. That is I is equal to integral h dot dl. So here we have only phi component. There is no component of h in rho and z. Only we have the phi component. Okay, it's like a circle. We have only phi component. So h, it is h phi a phi dot dl. So dl is equal to rho d phi a rho, where a phi cap and a rho cap, they are the unit vectors. A phi cap unit vector along phi direction and a rho cap is a unit vector along rho direction. So simplify this, you will get it like h phi integral 0 to 2 pi rho d phi. That is equal to h phi 2 pi rho. Simplify this, I is equal to h phi 2 pi rho. That is h is equal to 1 by 2 pi rho a phi. So we have determined the magnetic field intensity at a particular point if the current distribution is line current with the help of Ampere's circuit law. Second case, infinite sheet of current. Applying Ampere's law to an infinite sheet of current. So consider an infinite current sheet in Z equal to 0 plane, and if the sheet has a uniform current density K, where K is equal to Ky Ay and it is in the direction of Y. And here the rectangular box 1, 2, 3, 4, 1 represents the Amperian path. So for applying Ampere's circular law to this Amperian path will give us closed integral h dot dl is equal to current enclosed, and that is equal to Ky into B, where Ky is the current density along y direction and B is the length along x direction. And to evaluate this integral, let's consider the infinite sheet as comprising of filaments. And dH can be evaluated above or below the sheet due to a pair of filamentary currents. By looking into this figure, it is clear the resultant dH has only x component. It has only x component, and h on one side of the sheet is a negative of that on the other side. So we can consider, due to the infinite extent of the sheet can be regarded as consisting of such filamentary pairs, so that the characteristics of H for a pair are same for the infinite current sheet. And from this figure, it's clear that it has only x component. So the magnetic field H can be written as H is equal to H0 AX for Z greater than 0. This is the Z axis. For Z greater than 0, H is equal to H0 AX. And for Z less than 0, H is equal to minus H0 AX. It is H on one side is the negative of that on the other side. Now let's apply the Ampere's circular law. We know closed integral H dot dl must be equal to current enclosed. And now let's evaluate the closed integral H dot dl. That is the point where we stopped. So let's evaluate this integral. So here we have to consider the Amperian path, and for us that was a rectangular box. So the path is from 1 to 2, integral from 1 to 2 plus integral from 2 to 3 plus integral from 3 to 4 plus integral from 4 to 1 h dot dl. So let's evaluate this. So that's is equal to minus of, that is first one, 1 to 2 h dot dl is equal to minus hz minus a plus minus hx minus b plus hz into a plus hx b. So let's substitute values for this. That is equal to minus hz, that is equal to 0, that is equal to 0 into minus a plus minus h0 into minus b plus hz 0 into a plus h0 into b. That is equal to 2h0b. Here the z components nearby, they are equal and opposite and they cancelled each other. So just by evaluating the integral h dot dl, we got closed integral h dot dl is equal to 2h0b, where b is the length along the x direction. So from equations 4 and 5, we will get closed integral h dot dl is equal to 2h0b, that is equal to kyb. So here h0, it is still unknown to us. That was just arbitrary value that we have taken. So solving this equation number 4 and 5, we will get h0 is equal to 1 by 2 ky, where ky is our current density. So just we have summarized just before, we get h is equal to For z greater than 0, that is h0 ax. So that is 1 by 2 ky ax. And for z less than 0, we mentioned h is equal to minus h0 ax. So that is equal to minus 1 by 2 ky ax. So already we said the h will have only x component. That is why we have the unit vectors ax. So for an infinite sheet of current density k ampere per meter, the magnetic field H can be written as 1 by 2 k cross an, where an represents a cap n is a unit normal vector directed from the current sheet to the point of interest. So this is how we apply Ampere's circuit law to an infinite sheet of current to determine the magnetic field intensity. There is one more topic, that is applying Ampere's circuit law to an infinitely long coaxial transmission line, that I am giving it as a homework to my students. Do try it by yourself and let me know. So this lecture introduced the topics Biot-Savart's law, Ampere's law and its applications. And I have referred the textbooks Elements of Electromagnetics by Matthew N. Sadiku. Thank you.